So, I want to talk about what some of the final forms might look like when you've done, when you've put it into reduced row echelon form. Right? This is the process that we call Gauss-Jordan elimination. Right? So, if you have a system with two equations and two variables, then what you're going to start out with is an augmented matrix that looks something like this. Right? In reduced row echelon form, you're going to have one of three things. There's only three possibilities. You could have, let's say, 1, 0, 0, 1, and call this maybe PQ over here. Right? This is one possibility. When you do all your steps, you end up with this matrix over here and some numbers here. It doesn't matter what these are. These are going to be your solutions, actually. So actually here, we can even say, let's say our variables are x1 and x2. These are going to tell us that our solutions are x1 equals p, x2 equals q. All right, remember how we form one of these matrices from a system of equations? We're just doing that backwards here. First column represents x1, second one represents x2. The line is the equal sign, and these numbers over here are just some constant. Right, so this is one possibility. Another possibility that you could have is something like this. You could have 1 m p 0, 0, 0. Okay? You could have something like this. This one over here was one solution. This one here is going to be infinitely many. Right? When you have this row of all zeros here. Okay? So what does our solution look like here? Well, if we translate this back to a system of equations, we get x1 plus m x2 equals p. And there's really no second equation. It's just 0 equals 0. We'll ignore it. So what we have to do here is use a parameter. Since x1 is really easy to solve for here, right? It's going to be p minus mx2. What we do is we say, well, set x2 equal to t, and then x1 is just p minus mt. And that's going to be that solution. Okay. The third case that we could have will turn out to be 1 mp. So the same thing up here, but down here, 0, 0, q. Right? And I want to emphasize here that q is not 0. If we have this situation, this bottom row tells us 0 equals q, or 0 equals something that's not 0. So this is no solution. So it gets a bit harder from here to say, list out all the different possibilities. Right? For here, these small 2x2 ones, it's pretty straightforward. When we get to bigger systems, like say 3x3, there's a lot of possibilities that can happen. So I can't really give you a concise table with all of them anyway. But let's look at a few general rules, general guidelines here. So if we have, so I'm going to call these guidelines. And I want to call them guidelines because you shouldn't treat these as like hard and fast rules, right? What do I mean by this? Well, like just because you satisfy the guideline here doesn't necessarily mean this is going to be the answer. Right? So here, some guidelines are if more equations than variables, right? So this might be something like having 3 equations but only 2 variables, right? So if there's more equations than variables, I'll say there tends to be no solution. Right? Now again, I want to say there tends to be no solution. It is possible to have a solution. So possible solution. Or solutions, if there's infinitely many. If there are rows of zeros. Right? The only way to have solutions in this is if you have rows of zeros. Right? If you can reduce it and you get rows of zeros. Alright? Another thing is if there's more variables than equations. Right, now this thing here is actually always true no matter what. There is either no solution, or sorry, no solution, or infinitely many. So up here, this first one, when we look at it as a matrix, this is the number of rows is greater than the number of columns. Right? And I want to emphasize when we're counting this, when we're looking at the number of columns, this is not counting the constant column. Right, the constant column being this one on the right side of the line. Okay? Right? So the last column, we're not counting that one. This one over here is the number of rows being less than the number of columns. And again, same deal, not counting the last column, right? The constant column. So that's some general rules on like how many solutions there are and kind of what your solutions look like. Maybe we'll look at, let's say, going back to these examples from earlier. We'll just write a few of them down here actually. Let's look at some examples from earlier, or just some examples in general. So this here, actually I want to do things that are not 2 by 2 here. Right. So this thing here is one solution. So here we have x1 equals 1, x2 equals 2, x3 equals 3. Right, so this is our one solution here. Now it's typically a good idea to write your solutions in the form x1 comma x2 comma x3 equals 1, 2, 3. Right? Something else that might happen. Here's an example of something with only one solution. Right? This thing here, here's an example of more rows than columns. We need this row of all zeros on the bottom in order for this to have a solution. The solution here would be x1, x2. Right? This first equation is x1 equals 3. Second one is x2 equals -1. Let's look at another example here, just to show you another oddly sized one. Let's look at something like 1, 4, 0, 0, minus 3, 0, 0, 1, 0, 2, 0, 0, 0, 1. Right? This one here gives us x1 plus 4x2 equals -3, x3 equals 2, x4 equals 6. So notice here, we know x4 and we know x3, but x1 and 2, they're kind of stuck together. Again, this is an example of infinitely many solutions. So we'll solve for x1 here. And then what we're going to do is set the parameter x2 equal to t. And then our solution, 1, x2, 3, 4, is -3 minus 4t, t, 2, 6. And again, it's always a good idea to try and think of this as a constant part plus a parameter part. So we split them according to the ones with t's and the ones without t's. We get -3, 0, 2, 6, plus the stuff with t is -4, 1, 0, 0. Just want to give you an idea of a few shapes here. Right? So generally speaking, if we have things like what's going on right here, where, well, this column is an interesting one. Notice our staircase of these leading ones. Here are the leading ones. Notice how this staircase has a double wide one here, one that has an extra, it's a 2-column wide step. Whenever you see that kind of stuff and you have a solution, then this is an indicator of infinitely many solutions. Okay? The way I like to think of this is any column that doesn't have a leading one, like this, right? So all 3 of these columns have a leading one, but this one doesn't. This tells you that this is where your free variable is. And free variables, these are the ones we set equal to t or s, etc. Right? Depending on how many we have. Usually we start with t, then go to s, and then u is usually 1. I mean, you just use whatever letters you want, really. Right? So anytime you see columns that don't have a leading one, those are the columns that are going to be your parameters. Right? And this is the beautiful thing about making sure you have not just a row echelon matrix, but a reduced row echelon. As long as you cut it down to that form, you can pick out these leading ones, you can pick out these free variables, which are your parameters, and then it'll make it really easy to write down the solution to your system of equations. Okay. So I'll leave this video here, and then we'll work on an example in the next video.